Greetings and welcome to the Introduction to Astronomy. In this episode of New Discoveries in Astronomy, we will talk about how NASA's Cold Atom Lab aboard the International Space Station is creating one of the coldest forms of matter ever produced, allowing scientists to study quantum behavior that is normally hidden from view. So let's get started. How do scientists study the strange quantum behavior of matter when the constant motion of atoms normally hides it? Every atom around us is constantly moving. At ordinary temperatures, that motion overwhelms the subtle quantum effects that govern matter at the smallest scales. To reveal those hidden behaviors, scientists must remove almost all of the atom's thermal energy by cooling them to temperatures only tiny fractions of a degree above absolute zero. At these extraordinary temperatures, the wave-like nature of matter begins to dominate, revealing behavior that is normally hidden by heat. Inside NASA's Cold Atom Lab, scientists begin by heating small amounts of rubidium or potassium metal to create a cloud of atoms inside a vacuum chamber. Carefully tuned lasers remove tiny amounts of energy from the moving atoms, causing them to slow dramatically. Additional magnetic fields cool the cloud even further until the atoms enter an unusual quantum state known as a Bose-Einstein condensate, or BEC. Rather than behaving like billions of independent particles, the atoms begin acting together as a single quantum matter wave. This allows scientists to observe quantum behavior that is normally hidden by the random motion caused by heat. Scientists can create Bose-Einstein condensates on Earth, but gravity quickly limits how long they can study them. As soon as atoms are released from their magnetic trap, gravity pulls the cloud downward, ending the experiment within a fraction of a second. Aboard the International Space Station, however, the cloud remains suspended in microgravity. Researchers can observe the matter waves for much longer periods, cool them even further, and perform experiments that are simply not possible inside an Earth-based laboratory. The recent upgrade to the Cold Atom Lab expands these capabilities by improving the magnetic systems used to shape and control the ultra-cold atomic clouds. Why go to all this effort? Because these ultra-cold matter waves become extraordinarily sensitive measuring tools. Scientists hope that they can eventually be used to build quantum sensors capable of measuring gravity, acceleration, and motion with remarkable precision. Future matter wave interferometers may improve spacecraft navigation, study Earth's gravitational field, and even test some of the deepest ideas in fundamental physics. The goal is not simply to create colder atoms. The goal is to create better measurements. The upgraded Cold Atom Lab is now supporting multiple international research teams studying quantum physics in space. Its experiments are helping scientists observe the quantum behavior under conditions that cannot be recreated on Earth. At the same time, the laboratory serves as a testing ground for future quantum technologies that may one day support space exploration, planetary science, and precision measurements throughout the solar system. Sometimes the most important discoveries come not from looking farther into space, but from creating entirely new ways to observe nature itself. This discovery reminds us that astronomy and physics often advance by creating new conditions for making better measurements. By cooling matter to nearly absolute zero and studying it in the weightlessness of space, scientists can observe quantum behavior that is normally hidden from view. These instruments could help future spacecraft navigate more precisely, measure tiny variations in gravity, and perform experiments that test our understanding of the universe. So that concludes our discussion on NASA's Cold Atom Lab studies quantum matter in space. We'll be back again next time for another new discovery in astronomy. So until then, have a great day, everyone, and I will see you in class.